Hello, good afternoon. I am Kim Howell de los Reyes, a MS Computer Science student. So for this project, I will be discussing to you the three approximation algorithms. So as discussed in the class, we are given three variants on how to calculate or approximately calculate the value of pi. So for this discussion, I have used Java programming language. And we'll be also discussing the difference of the calculated pi value with respect to the actual pi value. And then we'll also discuss the frequency counts with respect to the input value. So we'll be showing you the trend between the input value or the size of the input with respect to the frequency counts. So for this one, this is the first variant. So essentially, this is just to get the pair of x and y's with respect to r. So we have x squared and y squared starting from 1 to r. So for all values in there. And then we check if the value is less than or equal to r squared. And then essentially, if that's the case, we increment in count. So that point is said to be inside the circle or the shaded region. And everything that goes greater than r squared are outside the shaded region. So we put here the frequency count here on line 13. So essentially, this counts the number of computation when you did the calculation of x squared and y squared. And then we'll show you the differences between the value of pi when this r value here becomes larger and larger. So when we start with r equals 100, we can see here that the value of pi tends to be at 3.1016. And with r equals 100, the number of frequency or the number of main computation that we had is 10,000. Okay, and then as we increase r, so let's say this is 500. So it jumps to 3.133392. Much closer to the actual value compared to when r is equal to 100. Then when we have r equals 500, we observe that the frequency tends to be 250,000. Then so let's try to increase the value of r and check the value of pi, the number of frequency as well. So after running this code again, so we can see here that the computed value of pi tends to be closer to the actual value of pi, which is 3.14159, etc., etc. This time we have 3.137548. Then the frequency tends to be equal to 1 million. Okay, so let's make it r equals 10,000. Let's just skip the value of r equals 500. So here we'll have 3.14119. So this is much closer compared to the value of pi calculated when r is just equal to 1,000. So meaning there are more x and y ordered pairs that tends to be located inside the shaded region. And then the frequency is 100 million. 1, 2, 3, 4, 5, 6. It's 100 million. Okay, when r becomes 10,000, the number of frequency tends to be equal to 100 million. Okay, then I'm gonna show you one graph. So this is for variant 1. I've already created in advance a graph wherein it shows you the size, the frequency count, and then the value of pi that's being computed given the size, and then its difference compared to the actual value of pi. Okay, so when size tends to go higher, the frequency count tends to go higher as well. Then, as we can observe here, the frequency count much looks like a quadratic trend. It's size squared. Since we are using size, or based on the code, we're using size twice. So we have used R in the for loop inside, and then we also used R in the outer loop. So that's why it's squared. So a quadratic function, or the frequency count is a quadratic function with respect to the size. And then the value of pi tends to be closer to the actual value, which is 3.1459. So as we can observe here, we have 2.76. Then it's increasing as we increasing and going closer to the actual value of pi when the size tends to get higher and higher. Okay, and at the same time, the difference tends to go lower when the size also increases. All right, so this is the growth of frequency counts versus the size. So the frequency count is n squared with respect to the size. So it's increasing in quadratic. And then, as we can observe here, the difference between the calculated value of pi with respect to the actual value of pi tends to get lower as the size increases. Right, so here, the size increases, and then as the size increases, the difference also tends to decrease. Okay, so that's for variant 1. However, we have another variant, which is variant 2. So essentially what's variant 2 doing is we create two random values for x and y, and then we just calculate if the distance of those ordered pair x and y is less than or equal to 1. Okay, so essentially if the distance here is less than or equal to 1, or if the condition here, the if condition is met, so we just increment the variable in count. So meaning that point is inside the shaded region. However, if the point is outside or greater than 1, so we increment the out count, or that point is not inside the shaded region. So most probably it's outside the shaded region. And then so we just simply put the frequency count here inside the for loop. So essentially, whenever we generate two random values for both x and y, we already increment the value for frequency count. Okay, and the formula provided to calculate the pi is given here on line 18, which is 4.0 times in count divided by the number of in count plus out count, or just this is just equivalent or equal to the number of points that have been generated. Okay, so let's start with n equals 100. So when n equals 100, so that's 2.92. Okay, so the frequency count is also equal to 100. Okay, so when we try to generate other random values, okay, it's 3.24, 3.32, as we can observe, it's 3.12. Some of the values tend to be, or the difference between the computed values and the actual value of pi tends to be larger. It really depends on the value that is being generated from the randomizer function of our math library. But whenever we increase the value of n here, as we can observe, so that's 3.088, 3.096, 3.18, 3.152. Okay, it's getting closer and closer compared to when we only have a few points, let's say only 10 points. 3.2, 2.4, 2.8, 2.4, 3.6. Okay. So as we increase the number of n points that we are generating, so let's say we have 10,000 points. So we'll be having a computed value for pi, which is much closer to the actual value of pi, which is 3.14159. So here we have 3.1356. If we try to run again, it's 3.148. Okay, 3.1556. And then let's say we have a million points. Okay, so given a million points, so that's 3.139. Okay, 3.1419. So this is more closer compared to the earlier values that are being computed. 3.1417, more closer. Okay, and then we also observe here that whenever we increase the size of n, the number of frequency counts also increases. This n value tends to be equal to the frequency count. Okay, and then so what I have here on the graph is a table. So for the computation of pi, I have created 3 runs, and then just get the average between those 3 runs. Right? For example, if the size is 10, so the frequency count is 10, and then for each run, I record the computed value of pi, and then just get the average. And then at the same time, when we get the value of pi, we get the absolute difference between the calculated value of pi and the actual value of pi. And then why is it that we only consider the absolute difference? Because we do not need the difference as a negative value. So sometimes the computed value tends to be greater than 3.1459. So we only consider the absolute difference between the computed value and the actual value of pi. So as we have here, it's 2.32. So that's a big difference. It's 0.82. Okay, and then with all the differences, we also get the average differences between those 3 differences with respect to these 3 runs. And then we do the same for all sizes. And then as we increase the number of size or the number of points being generated, we can observe that the value of pi that is being computed tends to be closer to the actual value of pi. Let's try looking here on size equal to 50 million. 500 million, sorry. So we can observe here that it's 3.145, 3.14156, 3.14154, 3.14147. Okay, and then as we increase size, as we double the size, we observe that it's getting more closer and closer to the actual value of pi. Okay, and then we compute the average using these 3 runs. Okay, so looking at the average, it's getting closer to the actual value of pi. Okay, then at the same time, we get the differences on the 3 runs and also get the average on the differences between these 3 runs. And as we can observe, the average difference tends to get lower and lower when the size also increases. Right, so here in the graph, we have the growth of frequency counts versus the size. The size is just equal to the frequency count. Okay, so it's linear time. And at the same time, this might look like quadratic because of the sudden change of value here. Okay, but we can just simply look at the table here showing the size and frequency counts. Okay, and then the average difference. So as we tend to increase the number of points that is being generated, the average difference tends to get lower and lower approaching 0. Right, so I did averaging of 3 runs. So to lessen the difference between the computed value of pi with respect to its actual value. Okay, so for variant 3, this is the third variant of the pi approximation algorithm. So what we're essentially doing is we convert the integer value from 1 to r to a decimal and check if that point for both, if that point containing x and y as an ordered pair resides inside the shaded region. Okay, and then we put the frequency count here. So the frequency count is put before which upon calculation of x squared and y squared. Here, this is x squared and this is y squared. Okay, and then just the same with the other approximation algorithms. We simply add the squares of both x and y and compare it to 1. If that's less than or equal to 1, we increment in count, or essentially the pair is inside the shaded region of the circle. Okay, and then here we have the formula to count the value of pi, or probably just to approximate the value of pi. It's 4.0 times the number of points divided by r squared. Okay, and then we just put here 1.0, so the value here r will automatically be considered as a floating point value. Okay, so let's start with r equals 100. So as r becomes 100, the value is 3.1016. Difference is approximately 0.2399. Okay, and then the frequency count is also the square of the value of r here. Okay, r is the input size, it's 100, and the number of frequency count is 10,000. Okay, let's see if we increase r to 1,000, the value of pi being computed is 3.137548, and the value for the frequency tends to be a squared of the input value, which is 1 million. Okay, let's put on 10,000 for r and observe the value for pi, the computed value for pi, if it will be closer to the actual value. So we have here this one. The previous value of pi when r is 1,000 is 3.137548. Comparing it to 3.1411, it's much closer compared to the earlier value of r. Okay, and here the number of frequency count is 10 million, 100 million, 100 million. And let's check if r is equal to 100,000. If r is equal to 100,000, just copy this one. Okay, and observe if the value of pi is being closer to its actual value. Again. So it will probably run longer compared to the smaller values of r, since we have here r equals 100,000, so we're expecting that the number of frequency count tends to be 10 billion. And then the value for pi is 3.14119052 for 10,000 value of input size. We'll probably show the value here after a few minutes. But I've already taken into consideration having all the values for the computed value for pi for some values of r. So I've already made a graph here. So that's 10, 50, 100, 500, 1,000, 10,000, 100,000. Okay, and here the frequency count is also the same as variant 1. So it's n squared. Okay, it's the quadratic function with respect to the size. And then the value of pi here tends to be closer and closer with respect to its actual value. Okay, because as you can see on the difference, as we increase the size of pi, the difference tends to be lesser and lesser, approaching 0. Okay, so this also is showing you a graph with containing the relationship between the size and frequency count, and below is the difference between the actual or the computed value of pi with respect to its actual value. Okay, and as we can observe here, same to variant 1, as we increase the value of pi, as we increase the input size, the difference tends to be lower now. Okay, so that's all for the pi approximation algorithms. So for the first variant is almost the same as the third variant. Okay, and the only thing different here is the second variant, since the values for x and y here are being randomly generated. So that's why the value for pi tends to be different between several runs for the same input size. Okay, so again, that's all. I'm Kim Howard de los Reyes, and thank you for listening.